We are now going to look at the concept of inductance. Let's first recall our discussion of capacitance and capacitors. So a capacitor is two conductors that you attach a voltage to. And we define the capacitance as the ratio of the charge on the capacitor to the voltage you are applying. Another way to think of capacitance is that it's the total electric flux emanating from the positive conductor divided by the potential. So in analogy to capacitors, let's look at inductance. Here I have a coil of one turn, and with the current flowing through the coil, we know the form of the magnetic flux density fields. We will define inductance, and we'll use the symbol uppercase L for inductance, as the ratio of the total magnetic flux over the current that's generating that magnetic flux. So the units of inductance will be Webers over amps, and this unit is also referred to as a Henry, which is named after Joseph Henry, who we will encounter when we discuss Faraday's law and electromagnetic induction. Since every magnetic flux line goes through the surface whose perimeter is defined by this current, we can find the total magnetic flux by finding the magnetic flux going through this surface. Here is our one-turn coil with the current I flowing around it. And let's think of a current element, IDL, and we will use the Savart Law to determine the magnetic flux density field at some point here inside our coil. I will use the sub 1 on our magnetic flux density field to indicate we're finding the magnetic flux density field for our one-turn coil. So here is the Savart Law, and R is the vector pointing from IDL to the point where we want to find the magnetic flux density field. We will use superposition and sum up the contributions of each IDL segment all the way around our one-turn coil to get the total magnetic flux density field at each point inside our coil. If we integrate B1.ds over the surface whose perimeter is defined by our coil, we'll get the total magnetic flux coming from this one-turn coil. We'll call that psi sub 1. Then our inductance for this one-turn coil is this calculated magnetic flux divided by the current that's generating the flux. Self-inductance refers to the inductance when we have just one coil, but we'll usually just refer to this as inductance instead of saying self-inductance. Now let's form a coil of n turns. So we'll have the same cross-sectional area as our one-turn coil, and we'll have the same current I flowing through it. We can again use the Savart Law to find the magnetic flux density field everywhere inside our n-turn coil, but now we're going to have to integrate around n times. So our resulting magnetic flux density field for the n-turn coil will just be n times the magnetic flux density field of the one-turn coil. If we integrate B sub n dot ds over the surface whose perimeter is defined by our coil, we'll get the total magnetic flux psi sub n. And we see that this psi sub n will be n times the magnetic flux we obtained from the one-turn coil. At this point, the inductance of our n-turn coil is not intuitively obvious. We would want to think it is the total magnetic flux divided by the current, but it is actually the number of turns times the total magnetic flux divided by the current. This result cannot be explained, it's just a description of what's experimentally observed. It will be straightforward to show this experimental observation when we talk about electromagnetic induction. This product of the number of turns times the total magnetic flux inside our N-turn coil is given the symbol lambda and is referred to as flux linkage. Substituting for psi sub n, n times psi sub 1, we get the inductance of our N-turn coil is n squared times psi sub 1 over I, which is the inductance of our one-turn coil. If we had a one-turn coil and its inductance was 1 Henry, if we then made a 10-turn coil, the inductance would not go up to 10 Henries, but it would go up to 100 Henries. Before looking at some examples of calculating inductance of various structures, let's introduce the concept of mutual inductance. Here we have two coils, coil 1 and coil 2. With the current flowing through coil 1, I sub 1, a magnetic flux density field is generated everywhere, and some of that magnetic flux will go through the surface whose perimeter is defined by coil 2. So we can use the Savart Law to determine the magnetic flux density field generated by current I1 everywhere inside surface S2 here. So psi sub 2,1 will be the magnetic flux through surface S2 caused by current I sub 1 flowing in coil 1. The mutual inductance will be defined as the flux linkage, that is, the number of turns of coil 2 times the flux going through surface S sub 2 originating from coil 1 divided by the current flowing through coil 1.